Two. And our first speaker now is Hinze Hogendoorn from the University of Melbourne. He's a senior research fellow at the School of Psychological Sciences and heads the Time and Brain and Behavior Lab. And as the name suggests, he works on, or tries to figure out how the brain works in real time, and especially how it compensates for its own delays. And he'll give a talk titled Predictive Visual Motion Extrapolation Emerges Spontaneously and Without Supervision from a Layered Neural Network with Spike Timing Dependent Plasticity. So Hinze, take it away.
Thank you very much, Christoph, for that kind introduction. And thank you to Neuromatch and everyone who's attending for being here and for your interest. Okay, so just to give you a background, so to sketch out the problem, right? So this is Roger Federer at the Australian Open, and he's playing tennis, and I'm sure that's familiar to you all. But one of the core challenges of tennis is that the ball can be served by many professionals at upwards of 200 kilometers an hour. And at that speed, it takes, the ball travels about 55 meters in a single second, which means it takes roughly 400 milliseconds to cross the court. Now, 400 milliseconds to cross the court. Just to give you a bit of context about that, it takes approximately 60 milliseconds just for visual information to get from the retina to primary visual cortex, ignoring any subsequent processing that might need to happen. In that time alone, the ball has traveled 3 meters or more. And if we're thinking of object recognition areas like inferior temporal cortex, we're thinking about 170 milliseconds, which means that in a very real sense, someone who's trying to return a serve at a Grand Slam is seeing the ball approximately 9 meters or more behind where it actually is. So clearly the brain cannot operate and act on the position where it sees the ball. So how is it that it is able to allow us to actually play tennis? Now, you might probably share my intuition that prediction and predicting where the ball is in the present effectively, or where it will be in the near future is probably part of that answer. But how might our visual system learn to use prediction to compensate for its own neural transmission delays? That's the key question I want to address in the project I want to tell you about. Okay, so prediction is obviously a word that we see a lot in current cognitive neuroscience, and predictive coding is a term that comes around a lot. And I'll just talk you through one of the main influential models. This is the Rao and Ballard model from 1999 with predictive coding, where there's this hierarchical system where there's input, let me just get rid of that. There's the input over here. It comes into this first layer, and the signal is fed forward to the second layer, where a prediction is formulated about what that input actually is. And then that prediction is then fed back to the first layer, where it's compared to the input, and the subsequent information that's fed forward is only the difference between the prediction and the input. And this happens at every layer, such that error signals are fed forward and predictions are fed back. And the core organizing principle of this is that the whole network sort of converges on a way to minimize prediction error. Now, the funny thing about predictive coding, to my mind, is that it isn't predictive in the sense that I use the word prediction, of meaning that it predicts the future. Predictive coding doesn't predict the future. Higher levels predict hierarchical lower levels, but they don't predict the future input of those lower levels. And that actually has a very important consequence, that for any time variant input, feedback predictions become outdated, resulting in prediction errors. But what we've previously shown is that it's possible to extend this model to deal with these neural delays, resulting in a real-time temporal alignment hypothesis. Now, what does that look like? If I look at this model over here, this is a model with successive hierarchical processing stages on the vertical axis and an object moving from left to right on the horizontal axis. And you see that in classical predictive coding, as information gets fed up the hierarchy, it becomes outdated relative to the new position. And also at every level where there's feedback projections, there is prediction error because the feedback predictions are mismatched new incoming sensory information. Now, what we can do is we can fix that by implementing extrapolation at every level. And if we posit that there's extrapolation at every level, actually the whole brain becomes aligned in real time. For details of that, I'll refer you to this paper, but here we want to ask, how would a neural network learn to do this? So how might a neural network learn to extrapolate? Well, let's start with things that we know to be true. We know that the visual system is hierarchical, and we know that one of the learning rules that operates in primary visual cortex is spike timing dependent plasticity. Now, spike timing dependent plasticity is a Hebbian learning rule whereby the relative timing of input spikes and output spikes at a synapse determines the potentiation or depression of that synapse. And basically what happens is that a spike that comes into a synapse shortly before the postsynaptic neuron is activated becomes potentiated, becomes stronger, and a spike that arrives at a synapse after the postsynaptic neurons become activated causes that synapse to become weaker. And that potentiation or depression function looks a little bit like this, where this line is the time of coincidence, and here input arrives earlier, and here input arrives later. So what does that mean for motion? Let's have a look. Here's a toy example of a toy neural network where there's these 5 level 1 neurons that project to a level 2 neuron that has a slightly bigger receptive field. And the level 1 neuron sees this little black object moving rightwards like this. As that black object moves across this screen, it'll trigger action potentials at each of these cells, which then project to level 2. Now let's imagine that these 4 inputs are enough to cause the level 2 neuron to fire. And then after the level 2 neuron fires, here comes the last level 1 neuron. So what's happened is that the object has moved through this receptive field and it's caused the level 2 neuron to fire. But this last input over here arrived afterwards. So what is going to happen to each of these 5 synapses up here? These ones are going to become relatively strengthened because they arrived before the neuron became activated. And this one is going to be weakened because it arrived after the neuron had fired. So what that does is that it causes the effective receptive field, which originally is symmetrical around these 5 neurons, to shift from where it is now towards to the left, because these neurons are getting strong, are more connected to that one, and this neuron is getting less connected to that one. So whereas previously this neuron would fire when the object was in this position, now the neuron is going to fire when the object is in this position. So effectively, it's still representing the same position, but it's firing for that position earlier. So effectively, it's extrapolating the future position of the object. That distance is the extrapolation distance. So we hypothesized that this might be happening in primary visual cortex. But what we then went and did is we went and modeled it in silico. So we made a neural network with 2 layers of neurons that have receptive fields a little bit like this. They're sensitive to position, and each of these neural populations is actually made of subpopulations tuned to specific velocities. So we'll consider separate subpopulations of different velocities, and then we'll show this network objects moving at a range of velocities. And what I'm going to show you is the evolution of the effective receptive field over time. So this is simulation time on the y-axis going from the beginning to the end. And here in the bright hot color is the center of the receptive field. And what you see is if the object is static here, that's this example, then the original receptive field here in blue and the final receptive field in the simulation in red are centered on each other. There's no shift, which is exactly what we would expect. Now, what's kind of cool is if we expose the network to moving objects, for example, here, this rightward object, what we see is that the receptive field gradually crawls to the left, exactly as what we would predict on the basis of spike timing dependent plasticity. And that shift actually gets bigger and bigger and bigger and bigger as we look at higher and higher velocities. So here, this blue curve again is the receptive field before learning, and the red curve is the receptive field after learning. So the neuron is learning to fire before the object arrives at the position that it originally coded for. So spike timing dependent plasticity in a hierarchical network. So these were level 2 neurons. The synapses of level 1 neurons synapsing on to level 2 neurons. Causes receptive fields to shift against the preferred direction of motion of these populations and effectively implements extrapolation. Now, what you can already see here is that this kind of scales with velocity. But if we look at that in a little bit more detail, we can see that velocity here on the x-axis causes a progressively larger shift of the receptive field that's very neatly obeys this logarithmic function, right? So the distance that the receptive field shifts increases monotonically, but with gradually diminishing returns as the stimulus velocity increases. And at this point, it's good to take a step back and think, well, what is the perceptual consequence of this receptive field shift? What this would do is that it would cause a static object and a moving object that are physically aligned to be perceived to be misaligned, whereby the moving object would then be perceived ahead of the static object. Now, that description matches perfectly with a visual illusion that we know in psychophysics called the flash lag effect, where, again, a flash is presented in physical alignment with a moving object, but nevertheless, there's the illusion that the moving object appears to lead ahead. Now, I've got a little video here to show you a demo of this, but I have no idea if this works over Zoom in this situation. What you see is this moving clock hand over here, and every now and then a black bar is flashed in physical alignment with the moving clock hand. And if this shows up on your screen as it does for mine, then you'll see that this flash bar appears to lag behind the moving bar and also appears to be bent at a slightly, I guess, older angle. So that phenomenon is called the flash lag effect, and many people have investigated that over the last 3 decades. And one thing we can do is we can compare how the flash lag effect depends, or the magnitude of the illusion depends on the speed of the moving object. And Wojtak and colleagues have done that in 2008, and they discovered that the relationship between image velocity and the perceived lag is also logarithmic. And actually, if we take our modeled receptive field shift data and their behaviorally measured perceptual data and correlate them to, if we find this correlation of 0.99, so it's near perfect, showing that spike timing dependent plasticity can cause shifts of receptive fields in velocity selective subpopulations. B, these shifts emerge spontaneously and without supervision and effectively implement visual motion extrapolation. And I want to sort of stress that this happens automatically. We don't make the model do this. The only things that we've started with are a learning rule that we know exists in primary visual cortex and the fact that the system is hierarchical. And we haven't injected anything else to make the model start to extrapolate. So the question is not really how might a model learn to do this. The question is more how would it not? It almost has to do this. And then finally, we show that this model shifts almost perfectly predict behaviorally measured perceptual shifts in the flash lag effect. So we've got a beautiful perceptual correlate to what we show in our model in terms of how the magnitude of the shift depends on velocity. And I want to just finalize by thanking my collaborators here. That's Tony primarily from biomedical engineering at the university, but also Stefan, Daniel, Tom, and Patrick, and all the members of my lab, Tessel, Philippa, Tim, Quiva, Jane, Charlie, and Chandel for their tireless work. Some of our funders, and of course the Neuromatch Conference for organizing this opportunity for all of us to get together. So thank you all very much for your time and your attention. I'm happy to take questions.
Well, thank you very much for this talk. Yeah, so if you have questions, put them in the Q&A window. Maybe I'll start with a quick question. So you have a very nice and simple mechanism here that underlies this shift. Have you thought about the implementation in the brain? So what neurons take part? I mean, we have these, which layer and so on. So yeah, if you can comment on that.
Yeah, that's absolutely a very intriguing question, and we spent quite a lot of time thinking about that. I'm hesitant to commit to an individual layer at this point because clearly we're simplifying the network, right? So one of the things we've clearly simplified is we haven't implemented any feedback connections, and that's one of the things we're currently working on, because I think my intuition is that those have a very important role to play into calibrating how much the neuron has to compensate for, because at present the network is essentially agnostic to how much the delay is between layers, and only through feedback we'll be able to identify what that delay is. And so once we just sort of get the cortical microcircuit figured out that might be able to do this, then I'll have a better grip on what layers are doing this. Currently, it's purely feed forward.
Okay, good, thank you. Any other questions? Oh, there is one. Okay, so Jeroen Smeets asks, despite the, I guess it should say shift, isn't the receptive field still responding with the position in the past? Right, so good question. So my take on it is no, the receptive field is, the level 2 neuron is essentially, its receptive field effectively shifts to where it starts to respond to an earlier position. So it actually starts to respond to the future position, or at least, you know, if you consider the rest of the brain reading out the level 2 neuron, it starts to respond as if that the object is already in the future position, where before learning, it would have to be to drive the neuron. Now it starts to respond before the object actually gets there. So it actually responds to the object in a future position effectively, rather than in the past position. Thank you. would also be consistent with this illusion you showed, right?
Exactly.
Yeah. Great.
And I'm very conscious that Jeroen has done some work, like very cool work on the flash-like. So I'd be very interested to take that discussion offline as well.
Yeah, so I think Nikola has posted some contact information in the chat. So if you want to talk offline, contact him. And well, thanks again for this very nice talk. So we'll move on to our next speaker. Our next speaker.